video for a unit on thermochemistry. We are going to be talking about heat. We're going to learn about temperature. We're going to be talking a lot about energy. So just to start off, I want to explain what thermochemistry actually means, and it's just the study of heat changes that occur during a physical and or chemical process. So the study of heat changes that occur during physical and chemical processes. Physical changes that could happen are both state changes and something like dissolving, which we talked about way back during first semester and at the beginning of the semester. Whereas chemical processes that we might be looking at involve burning or combustion or something like rusting. Remember, that was also a chemical process, which is not necessarily related to this unit, but just a reminder of what the difference between physical and chemical change is. So that is the study of thermochemistry. Before we really get into what we're doing regarding calculations and everything, I just need to go over some vocabulary. So the first piece of vocabulary is energy. And energy is the ability to do work or produce heat. Now, next year, you are going to be looking at the ability to do work with regards to energy, and that's what you study in physics. But this year in chemistry, we are all focusing on the production or transfer of heat as an energy source. Now, there's two different types of energy that we really deal with in chemistry. The first is kinetic energy. That's the energy of motion. Temperature is actually the measure of the average kinetic energy of particles. So the faster particles are moving around, the higher the temperature. If particles are moving more slowly, then the temperature is lower. And then we also have potential energy. Now, potential energy is usually stored in bonds, and it is due to the composition, which would be the storing in the bonds, or the position of an object. And it is actually what we also sometimes often in this class refer to as chemical energy, because it's stored in those bonds and it was released during a chemical process or reaction. So in order to understand everything from this unit, we really have to be able to know what the difference between heat and temperature is. So temperature, like I already talked about, is just the measure of the average kinetic energy of particles. And its symbol is represented by T. We've already used and talked about temperature this year. Heat, on the other hand, is the energy that transfers from one object to another due to temperature differences. And heat is always going to flow. That energy will flow from higher to lower temperatures. So we looked at that with our lab just earlier today or yesterday, and we looked at how our metal sample went and transferred some of that energy once we boiled it into our 25 or 50 milliliter sample of water inside of our coffee cup. So we saw that exchange of energy, and that was an exchange of heat. Now, the symbol for heat is actually Q, a little lowercase q. And so again, it is that transfer of energy. And so temperature is measured using a thermometer, whereas heat is measured using a calorimeter. Now, we haven't used a calorimeter, and yesterday we used thermometers, but we can also determine heat by using this new equation that we have right here, which is Q equals mcat, is what we often abbreviate it as. And it is Q equals the mass of something times the heat capacity, the specific heat capacity, which we're going to talk about on the next board, times the change in temperature. Remember that this little triangle or delta symbol represents change. So again, it's going to be heat equals the mass times the specific heat capacity times the temperature. And we're going to look more in detail what that's like on the next slide. The unit for temperature, as we know, is degrees Celsius. We've also dealt with Kelvin, but the official SI unit is degrees Celsius. Whereas the unit for heat, because we're specifically talking about energy, is joules or kilojoules. Now, also, sometimes you'll see it referred to as calories or kilocalories, but we're not going to use that in chemistry right now. So, now more in depth about specific heat capacity. As we saw, that is a part of our new important equation that we're going to be using today and the unit. The specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, we talked about this the other day when we were out on the pool deck. We talked about how water has this particularly high heat capacity. So it takes a lot of energy to heat it up, to raise the temperature, but it also holds on to that energy, which is really important. If something has a high heat capacity, it's going to take longer to cool off also. Now, the symbol for that is just a C or a C sub P. And it's important in the formula that we just talked about on the previous page. We have heat, which is going to be in joules, is equal to the mass, always in grams, times the specific heat capacity. And you will see, just like our gas constant last unit, the specific heat capacity kind of has some fancy units happening. And it's joules per gram degree Celsius. That's how we say it. So we would say the number is joules per gram degree Celsius. So, for example, the specific heat of water is going to be 4.184 joules per gram degree Celsius. And then our delta T is really the change in temperature, and that is equal to our final temperature minus our initial temperature, or TF minus TI. And that is always going to be in degrees Celsius. Q, I just really want to talk about this for a second. Our Q value, whether it is positive or negative, really tells us something about what is happening to that transfer of heat. Now, if our Q value is positive, that means our system absorbed heat, okay? So our lead or our metal shot transferred energy to our water, okay? Whereas if our Q value is negative, then it's going to mean that heat was actually released from that system. And we'll go in more detail and use that a little bit more in the future. Okay, so now we're going to go ahead and use our new equation that we just learned. And I'm going to do 2 different examples for you guys. The first example is somewhat already written out. If the temperature of 34.4 grams of water increases from 25.0 degrees Celsius to 78.8 degrees Celsius, how much heat has been absorbed or released by water? Now, just like all of our other word problems that we've done all year, the very first thing you need to do is go ahead and make your variables list. So I'm going to go ahead and label up here, and I already actually made our variables list right here, and then we'll write down our formula. But if the temperature of 34.4 grams of water, this is going to be our mass, which I already put right here, okay, increases from this to this. And so we can see that it says increases. So we know that this was our T initial. T initial was 25 degrees Celsius, whereas T final was 78.8 degrees Celsius. How much heat, this is my Q value, what I'm looking for, has been absorbed or released by water, okay? So all of my givens are right there already. Now, the one thing I talked about on the last slide was the specific heat capacity of water, and it's 4.184 joules per gram degree Celsius. I know right now you're like, oh, we have to memorize another thing, but we're going to use it so often that it's just going to be in your brain no matter what, and we will be okay with it. So, my whole variables list, I'm trying to solve for Q. What is that, what unit should I expect it to be in? Joules. You'll see that everything's going to cancel out except for joules. That's my brand new unit. We should be really excited about that. Then my mass is 34.4 grams of water. My specific heat of water, like I said, is 4.184 joules per gram degree Celsius. It's not going to be in here. If you are looking at something besides water, a substance besides water, you will always be given the specific heat of it. The water is the only one that we need to really memorize or be familiar with. And then my change in temperature, delta T, is going to be equal to my T final minus my T initial. So T final minus T initial. and that is 78.8 degrees Celsius minus 25.0 degrees Celsius. I round to my least known decimal point. I get 53.8 degrees Celsius. My brand new formula, the only one that we know so far, so this is easy so far, is Q equals MCAT. We can remember that because we all want to be doctors, right? MC delta T. All I got to do now, this is easy, I'm solving for Q. I just got to plug in. I don't even have to isolate any of my variables. So I'm going to say Q is equal to my mass, 34.4 grams, times my specific heat of water, joules per gram degree Celsius, times my change in temperature, which is 53.8 degrees Celsius, and I'm going to go through and cancel out everything that I need to. So my grams cancel out, my degrees Celsius cancel out, and I'm left with joules. Great, that's what we want, remember? So my Q, if I multiply this together, my Q value is equal to 7,743 joules. But I go back and I look at my initial stuff, and I have 3 sig figs, so I need to round. So I get 7,740 joules. Okay, so that is how much heat has been absorbed by the water, because this is a positive value. Now you can probably realize right away that the change in temperature is what is going to determine whether or not we are absorbing or releasing heat. Okay, so that many joules are absorbed. My second one, to what temperature will an 85.0 gram sample of lead decrease if it releases 2,080 joules of heat and the initial temperature of the lead is 193 degrees Celsius. The specific heat of lead is 0.129 joules per gram degree Celsius. So what I'm going to do is 85, my mass, Q is equal to, mass is equal to 85.0 grams. If it releases that many joules, this is my Q value. Heat and the initial temperature is, so T initial equals 193.0 degrees Celsius. Okay. 193.0 degrees Celsius. The specific heat of lead, so C sub P, is equal to 0.129 joules per gram degree Celsius. Okay, I am trying to find what temperature. Well, I'm trying to find T final. T final equals question mark. It actually equals delta T equals T final minus T initial. So T final is actually equal to delta T plus T initial. Okay? So I am first going to use Q equals MCAT. I'm trying to isolate temperature. So I'm going to say delta T is equal to Q divided by M times C. That is actually equal to 2080 joules divided by 85.0 grams times the 0.129 joules per gram degree Celsius. Okay, grams cancel out, joules cancel out, and I get delta T equal to negative 189.69 degrees Celsius. I'm going to round at the end. Delta, or T final, from over here, T final equals delta T plus T initial, which if I plug that in, I get T final equals negative 189.69 degrees Celsius plus 193.0 degrees Celsius, which equals 3.3 degrees Celsius. That is my